Good morning, good afternoon, and good evening, depending on the time you are watching this presentation. If you feel that there will be some areas where improvement is needed, feel free to comment so that we work on those areas. Hopefully, the next time we have a presentation, those areas will be worked on. So on this presentation, we are going to focus much on isoelectric, focusing electrophoresis. When we are dealing with isoelectric focusing electrophoresis, we need to understand to say that it is the method that is used to purify separate a mixture of proteins based on their isoelectric point. So we will be mentioning much of isoelectric point, so we should pay attention to this. So when we deal with isoelectric point, simply we are trying to mean the pH value at which the protein has the net charge of 0. So each point where the net charge of a certain protein is 0, that point is referred to as what? Isoelectric point. So we know to say that the human body has various types of proteins, and those various types of proteins, they are made up of 20 different types of amino acids, and of which 7 of those 20 amino acids in our body have readily ionizing side chains. So we are going to see how we are going to use those side chain groups in the in the separation or purification of the proteins. Okay, so these are the 7 now amino acids that are readily ionizable. So we have the first one, the aspartic acids, we have the glutamic acid, we have the lysine, we have the arginine, we have the histidine, we have the tyrosine, we have the cysteine. So now these are the amino acids we mentioned earlier. So now what we are able to see now from here, these are the ionizable, readily ionizable side chains. So now this is basically trying now to tell us to say that at a certain point there is a point whereby it will be negatively charged or it will be positively charged. So now this table here, it has about 3 columns, so to say, but not really columns, but let's just put them as in columns for easy understanding. So the first column is where we are finding the names of those amino acids, and then what will happen if maybe the pH is below a certain pH we are going to talk about, or the isoelectric point, or what if it is above. So if I mention that column 1, I mean to say the column where we are finding aspartic acid or the names of the amino acids. So if I mention column 2, I'm talking about now the column where it is below the isoelectric point. So the column 3, it's these structures at the far end there. So now let's try to understand what we tried to mean to say that they are readily ionizable. What does it mean? So we are going to give an example. So the best example, maybe the first example we are going to give about 2 examples. So the first one, let it be lysine. So this lysine, it has the side chain, the ionizable side chain, that actually changes depending on the pH. So let's say that our acid dissociation constant is 9.7, and of which that 9.7 happens to be the isoelectric point. We are expecting the lysine to have the net charge of 0. So now what does that supposed to mean? So that second column there and the third column, when we add the charges, we're expecting them to be 0. So let's say if the below the pKa or the below the acid dissociation constant, we have positive 2. We are expecting even above the acid dissociation constant to be negative 2. So once we add them, they are going to cancel themselves. But I'm not trying to say that they will be existing in two areas, being below the pKa and above the pKa at the same time. We are just trying to demonstrate. So for example, this one, as we are able to see, we are having NH3 plus, which is equal to NH2. So there we are supposed to have a negative. So now what is happening is here, we've seen arrows, they can go either ways, going towards the left and towards the right. So what is happening is here, depending on the situation, if we know to say that the isoelectric point is 9.7, we're expecting these charges to be equal. But now, the moment the isoelectric point is less than 9.7, we are expecting now that molecule or the protein to be more of positives. So a lot of positives will be in place. But now, when it is above the isoelectric point, it's going to also have the charge, where we are expecting the molecule or the protein or that amino acid to have more of negative charges compared to the positive ones. So that's what we basically mean there. We can also maybe try to talk about the cysteine. So again, the pKa for cysteine, let's say it is 8.3. So as we can see, the cysteine is the last row on our table, where it is having SH, where it is having the hydrogen there. So when we say that the cysteine 8.7, it's our isoelectric point, we are implying to say that the charges on the left as well as the charges on the right, once they cancel each other, our net charge will be 0. That will be our isoelectric point. Well, now, if it happens to say that maybe the pH is reducing, now it's less than 8.3, we are expecting now the charge on the left to be high compared to the charge, the negative charge. So if the pH now is more than 8.3 of the solution where we put cysteine, we are expecting cysteine to be more of negatively charged compared to what the negatively charged. But now, if we put it at 8.3, and of which we know to say that 8.3 is the isoelectric point, we are expecting the charge to be neutral. All the charges are going to cancel themselves. So, from what we've tried to explain here, there are some things we need to note. So, since proteins consist of different combinations of these ionizable amino acids, we are expecting now these proteins to have different net charges at a physiological pH of maybe around 7. So maybe if you just randomly pick any pH, maybe let's say that the pH of 7, we are expecting different types of proteins to have different charges because of the different combinations of those amino acids we've mentioned. What's another thing we need to note? It also means to say that each protein will have its unique pH at which the net charge will be equal to 0. Why? Because we have different types or different combinations of those amino acids. Okay, so now what is the principle of the isoelectric focusing? So we need to understand to say that all proteins have isoelectric point. So each protein has its own isoelectric point. So when maybe now we get a certain protein, we put it in a buffered solution at a constant pH, and we expose it. We expose it maybe to electrophoresis. We are expecting to say that there will be migration of that proton towards the opposite electrode, so long as the current is what? Flowing. And what will determine whether it will be moving, whether to anode or the cathode, it's the charge of the what? Of the proton. So let's say that we use maybe the pH gradient across the supporting medium, which is going to cause the proton to migrate to an area of a specific pH. The pH of the proton equals to a pH of the gradient, thus resulting in a sharp, well-defined proton band. We are trying to say that maybe let's say that we take a proton, we put in a certain supporting medium of which we have a gradient pH across that supporting medium. So now we are expecting that proton, that mixture of proton, to be moving. If we have about 3 types of protons in there, those protons will be moving, and each proton will go and set or formulate more like a proton band at a certain pH value. So now that same pH value we are talking about is what we are calling the isoelectric point. So when we are doing all these things we are mentioning here, maybe we want to determine the isoelectric point of a proton by maybe get a mixture of proton, we electrophorese that mixture of proton. We are going to see now the solution having a stable pH gradient in form of maybe anode and cathode, and of which that proton will start now migrating to the position in the pH gradient according to its isoelectric point. So now we are having 3 different types of protons. We put them in the mixture, we will put them in the supporting medium, and that supporting medium from anode to cathode, it's having a gradient pH of which we are going to see what we are talking about. It's having that. So as long as we expose that to a charge, we are expecting that to do what? To be migrating. And once they are migrating, each proton is going to now form more like a band, a proton band at its specific pH value. And that value is what we are calling as the isoelectric point. And the entire process is being referred to as what? Isoelectric focusing. We are trying to say that for example, about 3 types of protons. All those protons will now have different types of the isoelectric point. At those points, that's where now we are going to be observing the bands. Let's try now to see what we mean from this diagram that is being displayed at the moment. So what we are able to see now, it's the stable pH gradient. As you can see on top, we have numbers there from 0 to 14, of which as we are moving, so now where there is 0, if you observe, it's positively charged, which happens to be the anode. So as we are moving towards the cathode, we are seeing on top there that there is increment in terms of the pH. So basically that's how it is. So now those colored things we're able to see inside this supporting medium, they are protons. So now let's try to check how this is going to work. So imagine that orange, the red, the yellow on the anode terminal has been put there. So remember from the previous slides we said to say that once a proton is below each isoelectric gradient, it will be positively charged. We are able to see that that's positively charged. And the arrows, those arrows we are able to see just from top there, those they are showing now the movements, how now once the electric field has been applied, how those molecules now will be moving. So now they'll all be moving towards the cathode, if we see those that have been applied on the positive terminal. So if we have a look at the cathode end, we are having about two proteins as well. We have the purple one as well as the green one. They are negatively charged. Why? They are above the their isoelectric point. So in order for them to reach at their own isoelectric point, we're expecting them now to be moving towards the anode, not until they reach their isoelectric point. So now let's try to track how one molecule is moving. Let's start with the orange one. So from the first one, the first part, where we are seeing those three proteins on the anode, they are having about 1, 2, 3, 4, 5, 6, 7, 8 positively charged particles each. They are positively charged, and the charge is positive 8. So now that orange, it's moving. Let's try to observe now the movement. It's moving towards the what? The cathode. So now the second medium now is indicating to say that that orange one we are tracking only. Let's try to observe how the yellow one is moving. So now the yellow one is moving now towards the cathode, and there is something we need to observe there. The charge is changing. Instead of it having only positively charged ions, it is now we've seen the introduction of those negatively charged as it is moving. So now if we have a look at the last one there, let's observe how many charges. We have two positive charges and two negative charges. So now if we try now to cancel those, a positive with a positive will cancel each other, a negative and a positive, a negative and a positive will cancel each other, a negative and a positive again will cancel each other. And at this point we are going to say that the isoelectric point has been reached. So this is the point, out of which if we try to look, we compare with the pH gradient on top there, we can say to say that maybe approximately 7.9, 7.7, somewhere there. So that would be the isoelectric point for that molecule. So same applies with the, maybe let's try to get the green one. So the green one now, it was put on the cathode. So once it was above the isoelectric point, it was negatively charged. So again, the movement, we are seeing the arrow pointing towards the anode. So that's the direction to be moving. So the next point there, it is indicating. So the on top here, we only had negative charges. As we are moving now towards the anode, we are seeing now to say that there is one that one positive charge that has been introduced. As we go downwards there, it has also reached a point whereby we are having three negative charges and three positive charges. If we have a look, a positive and negative will cancel, positive negative will cancel, positive negative will cancel. So at this point, we're expecting now the net charge to be 0. So now if we want to determine the isoelectric point for this one, we may say to say that maybe it's 5 or 5.1, 5.2, somewhere that will be the isoelectric point for that green protein. So now let's have a look at the other part. Now we see how these things are moving, like where there is A, B, C. So now these A, B, C, imagine they are proteins that have been put in a supporting medium. Let's also remember to say that the moment we put them, that's the anode, ABC on top there, it has been put on the anode. So they have been put on the anode. What are the charges on the letters? They are positive charges. So as they are moving now downwards, they'll be moving as what? As cathodes. They'll be moving as cathodes, not until they reach their own what? Isoelectric point. If it happens to say that they were put maybe downwards on the cathode end, we are expecting to say that they will be moving as anions. They will be moving as anions towards the anode. They will be moving as anions towards the anode, and of which once the isoelectric point has been reached, we are expecting now that particular protein to stop moving. So one observation we're supposed to put in place is that the anode, as we can see, it has the lower pH, and then the cathode has the higher pH. So it is increasing as we are moving towards the cathode. So things we need to take from this: always, when a protein has been put uh, on the side where it is lower than its isoelectric point, it will be positively charged, and it will be moving or migrating as cations. So once it is moving as cations, it will be moving towards the cathode. Once it reaches the isoelectric point, the movements now will stop. Okay, what are now the advantages as well as the disadvantages for this now method of separating proteins? So when we talk about the advantages, we are saying to say that high resolution can be achieved. How is this now high resolution can being achieved? So as the protein bands are spreading, there is minimization of the spreading of those protein bands due to the application of the electric field and the pH gradient, hence us achieving the high resolution of what of hence us achieving the high resolution of those proteins. And another thing we need to observe is that proteins that differ by only maybe 0.001 pH units can easily be separated using this method. So one of the disadvantages is that the ampholites are used in high concentrations. So in order for this method to be successful, we are expecting us now to use the high voltage. So once the voltage is low, we are not expecting this method to be successful. So how can we use this method now? What are some of the applications? So some of the applications can be when we are trying now to separate proteins and peptides. We can also use this method when we are researching on enzymology, immunology, cytology, and taxonomy. So if we want to read more on isoelectric point, these are some of the references where the information I've put in this presentation was gotten from. So just appreciating the sources, I decided to say that I reference them. Otherwise, thank you for your time. Please, if any question, feel free to ask, and please tell me where you think that there should be improvement. I'll be more than glad to work on those areas that will be highlighted. Thank you very much.